Okay, so this is a continuation basically of your last notes. So I think the last heading was like periodic table or something, and these are still pertaining to the periodic table, so you don't need a new overall heading. But we are going to talk about different ways that elements can occur in nature and on the periodic table, and that we'll cover in chemistry. So the first thing we're going to talk about in these notes are the natural states. So the natural states are just how they occur in nature. Okay? So the noble gases, and remember the noble gases are in group 8A. So let's talk about that. If you have your handy dandy periodic table handy, you'll remember that groups 3 through 12 are called the transition metals, and they're the really big group down kind of in that section that's set in the middle, and those are typically also called group B. Okay, so group A is basically everything that's not in group B, which is the groups 13 or 3 through 12 on your handy dandy periodic table. So group 8A, if you're just counting the top columns, or like the columns, the groups that are raised, if you count all the way over, then you get that group 8A is the noble gases, or as we labeled them, it's also group 18. Okay, and these noble gases, they tend not to react, so they don't really react with anything. So they are found in elemental form, meaning that since they don't react with anything, they don't really form any other bonds, and so they won't be in a compound in nature. You'll find those elements in their elemental form in nature. What we call the noble metals, which are gold, silver, platinum, palladium, iridium, and rhodium. And these are some of the only metals that are found in the elemental state. Okay? Meaning you can find hunks of gold, hunks of silver, hunks of platinum just laying around in nature. And then let's talk about the diatomic elements. So di means two, and atomic, so it basically means there are two atoms or two elements that are bound together in nature. And one we talked about a lot previously, oxygen. So remember, oxygen in nature that we breathe is O2. Same thing for hydrogen, it'll be H2. Nitrogen, anytime we see it, will be N2. And fluorine will be F2. Same thing for chlorine, bromine, and iodine down here. So next, let's look at allotropes. And these are just different forms of the same element, meaning that they're still the same element, just bonded differently. Okay? We're going to highlight that because that's a definition. So for example, carbon, we know carbon exists in many different forms, and the most recognizable is diamond, which is just carbon compressed. And then there's graphite, which is also carbon. So basically pencil lead is graphite, and it's made of carbon. So why, if both of these are carbon, why is one so expensive and the other we use to write with? And same goes for soot. Soot is also carbon, like the black stuff that makes you dirty if you're like cleaning out your fireplace. All those things are composed of carbon, but they have very different properties, right? And the reason for that is the way that they are bound together. So a diamond actually is bound, it forms like a crystal shape, and so the reason diamonds are so strong is because the shape that the bonds make is so stable and so strong. Graphite structure, for example, they basically form layers, parallel layers on top of each other. So that's why we can write with it, because those layers just chip away. And soot really doesn't have a structure because it's very fine and made from breaking things down. And then this other man-made or synthetic allotrope of carbon is one called Buckminster fullerene. And that's probably the most unique one. And it looks like this. So its formula, I guess you could say, is C60. So in this molecule, it has 60 carbons that are bound together, basically to look like a soccer ball. Okay, moving on to ions. So these are how just elements exist in their natural state, in the elemental form. They're elements, they're not bound with anything unless it's themselves, in the case of diatomic elements. So let's start to talk about ions, because ions are an atom or group of atoms that carries a charge. So it could be a single atom, it could be a group of atoms that is going to carry a charge. And the magnitude and type of charge is going to be indicated by a superscript, so above, to the right of the symbol. For example, Na plus or 1 plus, and then sulfur 2 negative. And so remember, we have charged particles. We have protons, which are positively charged, and we have electrons, which are negatively charged. So the reason they get a charge is because they either gain or lose an electron. That is super important, so we're going to underline it. Due to gain or loss of electron. Not the opposite, not the gain or loss of a proton. We're strictly talking about electrons because electrons are what atoms can kind of share or get rid of because they're in the outer orbit. Remember, they can't really lose protons because those are in the nucleus and they're hard to get to. So there are two types of ions, and the first is cation. So cations are any positive ion, and that happens due to the loss of an electron, okay? They don't gain a proton, remember. They lose an electron, so they get less negative. So, for example, sodium, its atomic number is 11. So we know that that means it has 11 protons and 11 electrons. So just this atom of sodium, it doesn't have a charge because it has 11 protons and 11 electrons. So positive 11 plus negative 11 equals 0. So it doesn't have a charge. But a sodium ion loses 1 electron. So it still has 11 protons, but now it only has 10 electrons. So you have positive 11 plus negative 10, and you get a positive 1. So you'd say sodium 1 plus. These cations are typically formed by metals. So when we identified our groups on the periodic table, we know where the metals are, and those will typically form the cations. Like I have done already, the name of the ion is just the name of the element followed by the word ion. So I said a sodium ion. So that's for a cation, a positive ion. And the negative ions are anions. So the way I was taught to remember this, and it might be silly, but it'll help you, anions almost sound and look like onions. And if you eat lots of onions, your breath is going to smell kind of bad, and that's a bad thing. No one's going to want to be around you because your breath smells like onions. And so anions are the negative ion. And that is due to the gain of an electron. So they get more negative because they gained more negative particles. For example, we have sulfur here, and sulfur's atomic number is 16. So how many protons does it have? 16. And how many electrons does it have? 16. Again, positive 16 plus negative 16 is 0. So this is just an element, no charge, just sulfur. But a sulfur ion gains 2 electrons. So you have 16 protons still and 18 electrons. So you have positive 16 protons plus negative 18 equals a negative 2. So that's where we get the 2 negative up here on sulfur. Non-metals typically form anions. And this time the naming is a little different. For the name, you usually drop the last syllable of the element. So sulfur, you drop the fur part and just have sul, and then add ide. So sulfide ion. I included this note. You don't necessarily have to write it, but I do need you to remember it. So I need you to remember that you cannot confuse the ionic charge symbol, positive or negative, with the math sign plus or minus. So up here you didn't hear me say Na plus 1, you say Na1 plus. And the ionic charge of most, not always, but of most group A elements, so if you're looking at your handy dandy periodic table, group A, I'll remind you, is groups 1 and 2, and groups 13, 14, 15, 16, 17, and 18. So none of the transition metals, those are group B. Group A is everything else, and they can be determined by their position on the periodic table. So I'm going to give you time. Get out your handy dandy periodic table because we're going to mark these trends on the periodic table. I should see you with your periodic tables out because this is super important, and I promise it's going to save you some time. So now that you have your handy dandy periodic table in front of you, group 1, so hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium, those are going to have a +1 charge. So at the top of the column, just write a +1, and you'll know that those elements typically form cations, and they have a positive charge. So since they have a positive charge, are they gaining or losing which subatomic particle? Since they have a positive charge, that means they are losing electrons. Okay, they're losing a negative charge, therefore becoming more positive. So group 1 is +1 charge. Group 2, that starts with beryllium, magnesium, calcium. That entire group is going to form ions with a +2 charge, meaning that they'll lose 2 electrons. If we go on over to group 13, the boron group, so boron, aluminum, gallium, those are going to form a +3 charge. They're going to lose 3 electrons, so write +3 at the top of group 13 or 3A. And then the next group, group 4A, carbon, silicon, germanium, tin. You're going to leave that one blank. We're going to skip that one because it has different properties, so it is not always a certain charge. It could be a few charges, but we're just going to leave it blank for now. And we're going to skip on over to nitrogen, phosphorus, arsenic, group 5A. And that is going to have a charge of -3. So write -3 at the top. So now those elements tend to gain 3 electrons. Moving on to oxygen, sulfur, selenium in group 6A. Those, if you're noticing a trend, they will have a charge of -2, meaning they'll gain 2 electrons. They'll gain 2 negative particles. And for group 7A, fluorine, chlorine, bromine, iodine, they are going to form a -1 charge because they gain 1 electron, and then they're happy. And then last is the noble gases in group 8A or 18. And remember when we talked about the noble gases in their natural state, we said that they don't react with things, so they won't form, they won't like lose any electrons or gain any electrons because they're nice and happy, and so they will typically always not ever have a charge. So you can just write 0 at the top of group 8A, the noble gases. Okay, so hopefully you got those written because that is super important. I promise you will refer to that a lot. And so we can also call these polyatomic ions. And going back to our bioterm days, we know that poly means many, and atomic obviously means atom. So polyatomic literally means many atoms. So it's not just going to be one element, it's going to be many elements, many atoms. And they are going to be chemically bonded atoms and carrying a charge. Those are polyatomic ions. And if you still have your handy dandy periodic table out, you can flip it over and you'll notice the important polyatomic ion chart. So I'm not expecting you to have those ions memorized in your head permanently forever and ever. You'll be able to refer to that polyatomic ion chart. I'm sure you'll be able to remember quite a few of them because some of them are familiar, some of them are easier to learn. We'll be working with some of them frequently, so hopefully you can begin to memorize some of them, but you'll always have your handy dandy polyatomic ion chart. So now that we got ions down, let's talk about ionic compounds. So ions are just elements or an atom, groups of atoms that carry charge, but compounds are composed of a cation and an anion. Remember, cation is the positive ion, and anion is the negative ion. So in this situation, opposites attract. So the negative digs the positive, and it's due to the electrostatic attraction between them. So opposites attract. Since cations are typically metals, and since anions are typically nonmetals, Ionic compounds are typically found between metals and nonmetals. Just a few rules. The cation, the positive one, is always written first. The anion follows. So, going on to this bullet, the net charge of an ionic compound is 0 or neutral, even though it's made of charged particles. And I'm sure you're like, what in the world is happening? We'll talk about it. We'll do examples. So, in ionic compounds, the charge of the cations must equal the charge of the anions, because then the positives cancel out the negatives. So, we use the crisscross method when we write ionic compounds, or you can call it a chemical square dance, because basically, if we have sodium sulfide, so remember sodium has a 1 plus charge and sulfur has a 2 minus charge, you are going to move the magnitude of the charge, which the magnitude means just the number, to the subscript position for the other ion. So let's write that out here. We have Na plus sulfur 2 negative. So that means that you'll take the 2 down here and you'll take the 1 down here. But since it's a 1, are we going to write it? No, it's just implied. So we'd take the 2 down to the Na. So we'd have Na2, and then sulfur has an implied 1, so it's Na2S. And that is the quantity of the ions. So I'm sure you're like, well, wait, where do the charges go? How does this make any sense? We're gonna draw this out for you, and then we'll talk about it in class too. So if we have sulfur, let's zoom over here real fast. So we have sulfur, and sulfur has 2 negative charges. To cancel it out, to make it neutral, we can bring in, we know we have 1 sodium. And then how are we we still have this 1 negative charge here, so how are we going to solve that? The easiest way is to bring in another sodium. Okay, so to make them equal, to make the charge neutral, we need 2 sodiums and only 1 sulfur. Okay, and is that what we had written over here? Yes, we have 2 sodiums and only 1 sulfur, and their charges are canceling out. So what if the subscripts have the same magnitude? Well, you're going to go right here, and it says if the subscripts can be reduced, reduce them to the lowest whole number ratio. So if you had Mg2 plus and O2 minus, and you do the chemical square dance, bring those down, bring your partner round and round, you get Mg2, O2, and that's very redundant, so we just say MgO. Going on to the next one, if polyatomic ion is present and superscript is moved to subscript position on the polyatomic ion, add parentheses and write the subscript. Okay, so right here we just have a single ion, but right here we have a polyatomic ion because there's more than one ion present. So we have manganese and we have oxygen. This 4 is going to stay with that oxygen. So you have to put parentheses around it, like down here. This charge will still come down, and that imaginary one will come down, and you'll get MgMnO4 too. Okay? Basically, for subscripts on polyatomic ions, like up here, don't mess with them. You don't mess with them. They are married to that polyatomic ion. They will not leave. Okay? So this just talks about how ionic compounds may include one or more polyatomic ions. So it could just have one, like up here, or it could have multiple polyatomic ions. Going to the next page, we'll talk about isotopes. Now, isotopes, maybe you've heard of the word, maybe you haven't. We're covering it in chemistry, so it's fine. But isotopes are atoms of the same element with differing number of neutrons in their nucleus. So we know that they're still the same element because they have the same number of protons. They just have a different number of neutrons in the nucleus. So the other day when y'all were working on those worksheets and y'all were having to figure out how many protons, electrons, and neutrons there were, and you kept looking at the atomic mass, and the atomic mass isn't a whole number, and I kept saying, we'll just round it, and we'll talk about why it's not a whole number. Well, guess what? We're talking about why it's not a whole number, because the atomic mass is just the average weight of an element based on the abundance of its isotopes. Okay, so the mass number is the total number of particles in the nucleus of an atom. And remember that the particles in the nucleus are the protons and neutrons. So, since we can find the number of protons on the periodic table as the atomic number, we know that we can just subtract the number of protons from the mass number and get the number of neutrons. Okay? So, let's go down here to the symbols. Whenever we write about isotopes, we'll write the name or the symbol of the element followed by the mass number. So how many particles there are in the nucleus right there. So, for example, hydrogen has 3 isotopes. There's H1, H2, and H3. H1 has 1 proton, and so we know it has 0 neutrons because hydrogen's atomic number is 1 and its mass is 1. So if we subtract 1 from 1, we get 0. So it has 0 neutrons. H2, one of the hydrogen isotopes, has 1 proton and 1 neutron, and its mass number is 2. Okay, so hydrogen 2 has a completely different mass number. And then there's also hydrogen 3. It has 1 proton and 2 neutrons. So it has 3 total particles. But 99.93% of all hydrogen on Earth is hydrogen 1. Okay, so to find the atomic mass of hydrogen, they averaged how abundant it is together and did a really complicated math to figure out that, okay, most of them are this hydrogen 1 that has 1 proton and 0 neutrons. So they figured out 99.98%, which is nearly 100% of it, is this one isotope. But there can occasionally be H2 or H3 in very, very trace amounts. So when they averaged all of those together, they get basically 1, which is why most atomic numbers are not whole numbers, but hydrogen is like 1.008. Okay, so it's nearly 1. That's why I told you it's fine to round, because the atomic mass is just an average of the isotopes. Okay, so since hydrogen 1 is the most abundant at almost 100%, that's why the atomic mass is basically just 1. Okay? We're not going to start on this part right now. So as long as you've got everything for the isotopes written up to this point, you are good and done and finished with your notes. Good job.